when a massive star collapses under its own weight, creating a singularity, a point of infinite density at the center. Black holes have such strong gravity that nothing, not even light, can escape from them. They are invisible to telescopes but can be detected by their effects on nearby matter, such as the gas and stars that orbit around them. The study of these extreme phenomena is an important area of research in astronomy and astrophysics. They provide valuable insights into the physics of gravity, the behavior of matter in extreme environments, and the fate of stars and galaxies. They also challenge our understanding of the universe and raise important questions about the ultimate destiny of all matter in the cosmos. Stars are the engines that drive the creation of heavy elements in the universe. The nuclear fusion that powers a star's core releases energy in the form of light and heat, but it also creates heavier elements through a process called nucleosynthesis. As a star fuses hydrogen into helium, it also creates trace amounts of heavier elements like carbon, nitrogen, and oxygen. When the star runs out of hydrogen fuel, it can continue to fuse heavier elements until it reaches iron, which is the most stable element. The heavy elements created in stars are eventually dispersed into the surrounding interstellar medium, where they can be incorporated into new generations of stars and planets. This means that the composition of a star can reveal important information about the history of its galaxy and the processes that have shaped it over time. The study of stellar populations is an important area of research in astronomy and cosmology. Different types of stars have different lifetimes and properties, which can be used to date and characterize the evolution of galaxies. For example, the presence of old stars in a galaxy can indicate that it formed early in the history of the universe, while the presence of young, massive stars can indicate recent star formation activity. Stellar populations can also reveal information about the chemical composition of galaxies. The abundance of different elements in stars can be used to infer the history of star formation and the mechanisms that drive it. For example, the presence of elements like carbon and nitrogen in stars can indicate that they were formed in regions with high levels of star formation activity, while the absence of heavy elements like iron can indicate that the galaxy has not undergone significant star formation in a long time. Stars come in a wide range of sizes, temperatures, and luminosities, and can be classified into different types based on these properties. The most common classification system used by astronomers is the spectral classification system, which categorizes stars based on their spectral lines. A pattern of dark and bright lines in their spectra that are produced by the absorption or emission of specific wavelengths of light. The spectral classification system uses a series of letters to denote the temperature of a star, ranging from O, the hottest and most massive stars, to M, the coolest and least massive stars. The spectral classification system uses a series of letters to denote the temperature of a star, ranging from O, the hottest and most massive stars, to M, the coolest and least massive stars. Within each temperature class, stars are further classified based on their luminosity and size, with the largest and most luminous stars classified as giants and supergiants. Another important property of stars is their mass. The mass of a star determines its internal structure, its lifespan, and its ultimate fate. Low-mass stars, with masses less than about 0.5 times that of the Sun, will eventually become white dwarfs, while high-mass stars,